Okay, so yeah, thank you first of all to the organisers for the opportunity to speak. Can everyone hear me? Okay. No. Yeah. That's working. Sorry, I'll try and speak louder. So on Monday, Sikkering Yukong gave a talk on the variational principle for discrete one-dimensional systems, and Frank has given an overview of the general principle. So I'll be focusing on two-dimensional discrete integrable systems and giving a few more specific results in that case. And I'll try and be good and stick to discrete systems. So to be more accurate, I'm going to be talking about 2D multidimensionally consistent systems. And so we'll have lattice systems with firstly two independent variables, say L and M. And then, of course, for multidimensionally consistent systems, we can add in principle an infinite number of independent variables onto this. And we consider our system to live on any surface in this bigger space of independent variables. And so, oops, is this working? Yeah. So, in the usual variational principle, you have an action defined on this surface. And so you'll have an action defined on the surface. And this is critical points of the action is where you consider your system to live. So the question is, as Frank mentioned before, how can we get a variational principle to include this whole infinite dimensions and the system living on any surface in this lattice? So, well, we usually have an action defined on this flat two-dimensional lattice. We could define an action on an arbitrary surface embedded in this larger space. It's then natural to propose that the system should be derived from a variational principle, which includes not only variations with respect to the dependent variables, but also variations in this surface in the space of independent variables. This gives us a kind of answer to the problem of how do we encode this in a variational principle. Now this also puts constraints on the Lagrangian, both on the Lagrangian and on the equations of motion, on the Euler-Lagrange equations. And in particular in this two-dimensional case, it gives us a solution to the problem that for the flat two-dimensional problem, we could only get equations from this variational principle that were somehow of a weaker form than quad equations. So if we want to get quad equations from a variational approach, we need to invoke this bigger idea. Okay, so for anyone not familiar with variational principles for discrete systems, I'll just give a quick overview of this. So as a link to the continuous systems, we start with the premise that a system arises as the critical point of some quantity, which we call the action functional. So that is, so we have a path that we suppose the particle to, or whatever it is, to follow. We make an arbitrary small variation in this path taken by this dependent variable, and we require that to a first approximation the action is unchanged. So this is the usual variational principle. And so this idea has been around for hundreds of years. But it was only really in the 1970s that a calculus of variations was developed for discrete systems. And the main people in this story were Kadzov, Logan, and Maeda. Kadzov's original motivation, so this has nothing to do with integrable systems, his original motivation was the use of the digital computer in modern systems and the solution of control problems. And it became clear that the formulation of a discrete calculus of variations was very important for numerical methods in optimization and engineering problems. So in the discrete realm, instead of the action being an integral of some quantity, the Lagrangian, over the independent variables, it's now a sum. And as I said before, the one-dimensional case was described in the talk on Monday by Sikkering Yukong. And so I'll skip straight to the two-dimensional case. So for two-dimensional discrete equations, say defined on a quad, we can write an action the action S in this form. So it's 2 dimensions, so it's going to be a double sum over each independent variable and of some quantity, some Lagrangian. In principle, it could depend on more shifts. Yeah, I'm afraid I've changed notation again, sorry. We've got tildes and hats now to denote shifts in the lattice. It makes everything fit on the slide better. It pays to restrict to this case where you have a Lagrangian depending only on u tilde, and u hat. And you'll see why in a bit later. There are many results that you can get from this. Here, alpha and beta are at the moment just parameters associated with the various lattice directions. So, how do you get the equations from this? Well, the discrete Euler-Lagrange equations arise from the principle that the change in the action is 0 under small local variations of this dependent variable u. So here epsilon is small and phi is just some very arbitrary function. So the change in action, so this is the new action when you've varied u minus the old action. So this is the new Lagrangian. You do a simple Taylor expansion, considering that epsilon is small. And because you're summing over the entire lattice, you're free to shift this term back in the L direction and this term back in the hat direction. And so this is what we get. So we have this entire term multiplied by epsilon phi. And remember, phi was just an arbitrary function. So since we want the change in the action to be 0, to first order an epsilon, we must have that this term in the brackets is 0. And this is our discrete Euler-Lagrange equation. So up to this point, this is reasonably standard discrete variational principle. Not necessarily for integrable systems, just for discrete systems in general. So just as a quick example, the good example discrete potential KdV equation, the Lagrangian has this kind of form. And so this is one of the problems with this, that the discrete potential KdV equation is an equation on a single quad, whereas from the discrete Euler-Lagrange equations, we get essentially a weaker version. So this is one copy of the equation, and this is another copy of the equation. So the entire thing lives on 7 points, whereas it's 2 copies, one on this quad and one on this quad, of the discrete potential KdV equation. Sorry? Well, yeah, sorry, I haven't put any coordinates on there, but yes. Yeah, depends which way you take your coordinates, but yeah. Okay. So, so this is the new principle. So for multidimensionally consistent systems, we have a system of compatible equations on the same dependent variable. And we can consider this system to live in this much larger space of independent variables. So we think the variational principle should provide this whole system. So this was, we proposed first in this paper here. It was completed in the Newton Institute program in 2009. That multidimensionally consistent systems should be critical points of an action, critical with respect to the dependent variable and also with respect to the curve or surface in independent variables. And as I said, we require also small variations in the space of independent variables to leave the action unchanged. Okay, so we can define the action on a surface. So if we look at one particular quadrilateral in the surface, one way to characterize this plaquette is by an initial point n in the surface and 2 vectors, ei and ej. And then we can evaluate the Lagrangian on this plaquette. So for any plaquette in the surface, we can evaluate this Lagrangian function on it. So now this is a Lagrangian evaluated on a 2-dimensional object, so it's a 2-form. And then we can choose some kind of surface in this lattice, consisting of a connected configuration of these elementary plaquettes. And we can define our action to be the sum of the Lagrangian evaluated on each of the plaquettes in this surface. So the action now depends on the dependent variable u and also on the surface, in principle on the surface that we choose sigma. So if we want small variations of this with respect to the surface to be 0, we look at the smallest possible variation of the surface we can make. So if this is our surface, we can make a small variation, and we can choose this quad here and just pop it up. And so the action of this new surface will be the action of the old surface minus the contribution from this plaquette here, and adding the contributions from the plaquettes on each of the faces of this cube here. So this is minus the first plaquette, and then adding the contributions from each of the others. And these minus signs are taking into account the orientation of the plaquettes. So in particular, for this to be well defined, or for the action to be well defined, we required this Lagrangian to be antisymmetric with respect to the changes in the lattice directions. Okay, so if we want the change in the action to be 0, then we must have this relation. So this entire quantity here must be 0. So that's this expression here. And we can write this in a slightly more succinct form here, where this delta is a differential operator in whatever direction of the lattice is labelled here. So this is what we require to hold, this is what we require to hold on solutions to the equation. So the first thing to, the theory is all well and good, but the first thing to ask is, does this actually hold for examples? And the answer is yes. So in our first paper here, we showed that this equation held for the first few cases in the ABS list, and then later, shortly afterwards, this was proved for the full list of the full ABS list by BS in 2010. We also showed that this held for the lattice Gelfand-Dickey hierarchy, which is a multi-component system, and also for this other multi-component system that James Atkinson derived in this paper here. There's also analogous cases for 3-dimensional and 1-dimensional cases, but I won't go into that here. Okay, so we know that this holds for many examples. So what can we do with this? So as I mentioned before, the usual case for a quadrilateral equation with a 3-point Lagrangian, depending on u tilde and u hat, the normal Euler-Lagrange equations involve these 7 points. So we don't get a quad equation, we get this configuration of 7 points. And this gives us our planar Euler-Lagrange equations. That's given by this expression here, which we saw on the previous slide. So this was just taking a flat 2-dimensional space. So I should mention these results. If anyone was in the talk in Norway last month, this was presented by Frank Neo. And related results have appeared last week in this paper by Boll, Petrera and Suris, which I'm sure Yuri Suris will be talking about later on. So if we look at the action over a curved surface, we could have, for instance, if we're just considering this point in the center of the lattice, we're looking at all equations involving, or all actions involving this point. So if we had this point as a corner of this cube here, then the Euler-Lagrange equations will involve these points here. And then if we look at this cube over here, because this is remembering that the Lagrangian has a 3-point structure involving u tilde and u hat. So this would be involving these points here. And then if we look at this bottom cube here, in principle this would be a corner of the surface involving this back face here. But because of the 3-point nature, this plaquette doesn't actually contribute to the Euler-Lagrange equations. So we just have these points here. So what equations do these configurations lead to? So this is the first equation, this one. Oops, where are we? Here. This is the first equation. This will lead to this expression here. And then the second equation with some shifts will involve these here. and the third equation only has two terms because of this three-point nature of the Lagrangian. So that corresponds to this equation here. And the proposition is that this is actually an exhausted list of elementary Euler-Lagrange equations, because any other surface can be constructed as a combination of these, or these configurations are equivalently of these equations. So if we impose that the action remains invariant under perturbations of this surface, then in the discrete case, this must mean it's independent of the surface. We can't make arbitrarily small variations. We have to do our discrete variations. So it has to be independent of the surface. And then all of these equations must hold simultaneously. So one thing in particular to note, that this equation in flat 2D space that we had before is actually a consequence of these equations. So this equation here is a consequence of these equations. So just to see that this is an exhaustive list, we can consider an action of a closed surface. So the smallest non-trivial closed surface is a cube, for which the action is simply these 6 terms here. If we require variations of this action with respect to the dependent variables, of course, this time to be 0, then we get this set of equations together with some permutations of the lattice directions. So we have this for in the u hat and u bar direction as well. So shifting these in the lattice, shifting this one backwards in the lattice in the L direction, and shifting this one backwards in the L and M direction, or the tilde hat direction, we can see that these are entirely exactly the same as these equations here. So these are the only equations that we need. So yeah, any closed surface can be constructed from cubes. So at least away from the boundary, all possible Euler-Lagrange equations are consequences of these equations. So now we want to consider quad equations. Suppose we're looking for an equation on a quad, so an equation involving 4 points around an elementary plaquette. So we'll assume now, I've been assuming that the equation will have the same form for each pair of lattice directions, but I think that this could be easily generalized. So the first thing, the first constraint that this puts on the Lagrangian is that the Lagrangian must have this form, this 3-term form, for some functions a and c. The only constraint here is that c must be antisymmetric with respect to interchange of the lattice directions, just simply because L must be. And it's quite easy to see this. So if we consider the first equation, so that's this equation here. If we write this small l as the derivative of the Lagrangian with respect to u, then we must have this expression here. So all I'm doing is assuming that the Lagrange that we can choose initial conditions of u and its first shifts in each lattice direction independently. So this must imply this expression. So we must have L is the composition of these two functions here, for some functions a and b. So this, together with the cyclic permutations of the lattice directions, gives in fact that L must have this form. Now simply L is the derivative with respect to u of the Lagrangian. So we must have the Lagrangian involving so this is the integral of a, essentially, with respect to u. And we must have some term not involving u, so some term that just involves the tilde and hat. Yes, and yeah, as I said, because L must be antisymmetric with respect to the tilde and hat directions, that must mean we have C antisymmetric also. So note here that A is only defined up to an arbitrary function of u. So yeah, so first of all, this is the 3-term form of the Lagrangian. And the next thing to note is that the Euler-Lagrange equations, these set of 3 equations together, specify a relation on a single quad in the lattice. and that quad has this form here. So whereas I mentioned before, this HU is an arbitrary function that can be absorbed into the A. So we get the following equivalent equations. So this is one equation that we get. So the derivative with respect to U tilde of these three terms here must be 0. So this is entirely equivalent to this. And this looks slightly non-symmetric, but you can have an entirely equivalent relation here with derivative with respect to the U hat. So these are your equations on a single quad. I won't quite go into the proof of this because it's just very algebraic and not really very illuminating in a talk. But it relies entirely on the fact that you can choose U and the initial shifts in the various lattice directions independently. So examples of this. Well, if we just look at the example of H1, or the discrete potential KdV equation, the Lagrangian evaluated on a plaquette in, for instance, the ij direction has this form. Sorry, I've switched notation back again to the notation that Frank was using before. Then the Euler-Lagrange equation has this form, and by Euler-Lagrange equation I mean the one that we've derived here, and that has this form. So actually what you get is also an arbitrary lambda, but this is just because of the symmetries we imposed on the Lagrangian. You don't get the full D4 symmetry, you get an arbitrary constant lambda, but this is not a problem. This is still consistent around the cube, and everything works fine with this. Another example, taken again from the ABS list, if we use this Lagrangian here, then the Euler-Lagrange equation on this individual plaquette has these forms. Well, we get these relations here for some Ti and Tj. These relations together imply that Ti must be equal to Tj, and then so this has an arbitrary constant delta in here. If delta is 0, then Ti and Tj must both be 1. So we have the usual equation. This is exactly the H3 equation. If delta is 0, then we have just a tiny bit more freedom, and we can let the Ti and the Tj both be some arbitrary constant mu. And in that case, the equation has this point here, so the arbitrary constant mu is just coming in here. But yes, that can be scaled away, and the equation is still consistent around the cube with this anyway. Okay, so this is, so these are the equations that you get from this equation on the individual quad. Okay. So just to summarize, this multidimensional consistent systems, they can be considered as critical points of an action. So now it's critical with respect to the dependent variable, and also with respect to the curve, or in this case the surface, in the space of independent variables. And in this way, quad equations can be shown to arise from a variational principle, whereas previously only a weaker form of the equations could be derived. So this really seems to be a stronger principle from which multidimensionally consistent systems can be derived. So this principle leads to constraints on the Lagrangians of multidimensional systems, as well as the equations. So in a sense, the Lagrangians themselves can be considered as solutions of the system. This idea puts constraints on both the equations and the Lagrangians. So this may be a way of deriving Lagrangians, first of all, for multidimensionally consistent systems. It may even form a way of classifying systems on the level of the Lagrangian. Okay, so yeah, thank you for listening. I should probably stop there.
Any questions? Yes. Following your talk and the talk of Frank, and actually a few talks of Frank, I always have a feeling that that these relations, the closure relations, etc., that you observe should be not a property, but rather part of a definition of your Lagrangian. And that is one point. Another point, it's a strong feeling that what you're doing is you developing some, cohomology of a certain complex. And that should be a more natural way to formulate the problem, because these conditions you have would be part of a definition and fit each other. Of course, it is not the naive complex which been in the paper of Mansfield and Haydn, but variational complex. It is a different complex. Did you think in this direction? That is the first question. And second question is, look, you have these nice properties you observe with integrable system, but I believe the Lagrangian must be more general and suitable also for non-integrable systems. Do you have examples of non-integrable systems and Lagrangian which satisfy all your conditions, including, the closure relations?
Okay. So firstly, yes, your comment originally about this being more of a definition, yes, this certainly, we're kind of taking this as the original definition and then deriving the system from that. And then the closure relation is a kind of check to check that everything is consistent and everything works for these systems. The cohomology direction is not, it's something I've started to look into, but yes, that would be a direction to go further in. Yes. That would be a fruitful direction to go in. And sorry, your last question?
Last question was, what about, do you have any Lagrangian which fits all the bills, all the properties, but system is not integrable?
No. They may exist. I don't know. I don't have an example that fits all of the criteria and is non-integrable. This is I don't know. This is taking the definition of integral as multidimensional consistency. There is some arguments as to whether that's exactly the right criteria or not. But this is certainly for multidimensional consistent systems.
Any more questions?
I also have two questions, one for Sarah and one for Frank. Maybe I can start with Sarah. So, if I understand correctly, your second dot point there, you mean that instead of having a 7-point, getting a 7-point equation, you get a 4-point
equation? Yes.
Now, I guess my question is whether you could also do that for the KP case.
Yes. I don't know. I haven't tried yet. Because for that one you get several copies, you get 12 different copies. Yes, in the three-dimensional case you get 12 different copies coming from that. So I haven't investigated that case yet, but yes, hopefully that should lead to a similar result.
Well, then, if I may ask also a question of Frank. So in your talk you talked about these discrete variables, and then you also added continuous variables, with the continuous variables with the parameters. But of course, the independent variable also satisfies equations with respect to, if you like, the normal continuous variables. Like you can just get the continuous KDV for the same dependent. So my question is, can you include those as well in the?
Yeah, you can, but you don't need them actually, because in some sense that's why we call them generating PDEs. The equation in some sense generated by systematic expansions, the usual hierarchy. So they're kind of like Niva, and what we call Niva variables. Any more questions?
Sarah, you presented the proof of something, but I didn't catch what the theorem is. Could you please formulate precisely here?
So, well, I presented a couple of propositions. The first, there was, so one of them, which I didn't give a proof for, was that this specifies the relation on quad.
So, I would like to hear a precise statement.
Yes. Okay. Well, I'll start off. So, first thing, the Lagrangian has 3 points. So, it depends on.
What are the assumptions and what is this?
Okay. The assumption is that the Lagrangian should depend on u tilde, and u hat. And this is the first thing. It should be antisymmetric with respect to the change of the lattice directions. and also that you should be able to choose initial conditions on the lattice U together with the single shifts in each lattice direction, and you should be able to choose them independently and arbitrarily. So these are the assumptions that I'm making up.
Up, suppose.
Sorry?
Not that you are looking for equation on elementary plaquette.
Yes, that's the idea. Yes, and this is indeed what you get. You get these equations.
This maybe is more a remark than a question. To the extent that I understood this talk, it seems to me that this is a very nice definition of integrable systems. And this is, to me, very desirable, because I think that the standard definition of integrable system is highly defective. The standard definition of integrable system is correct mathematically, but useless.
Which one?
Which one?
There are many definitions.
Yeah, okay. Let's take a dynamical system, forget even Hamiltonian, and my definition will be that this system has the maximal possible number of independent constants of motion. Okay?
Yeah.
Well, this definition is, in my opinion, useless.
That's
But
correct.
it is useless because, for instance, the most general many-body problem with arbitrary number of particles, dimensional space, and forces, the only restriction that it is invariant under translations, so no external forces, with this definition, this system is integrable. So that leads me to think that this definition is not particularly useful. So if one has some other adjective like algebraic integrability, then that is useful, presumably, because it constrains the system. But the one based on conservation laws is useless. And by the way, the opposite is also true. The usual definition of chaos is also useless, because one can show that, well, I talk enough. I mean, that if people are not chaotic here, so. Oh, discrete, I think it's, I don't know, maybe it's the same. I mean, I think, I don't know. Yes, people here are discrete. I haven't thought enough about discrete, but I think it's analogous.
All right, I think this is a very interesting topic we could talk about,